It's the last minute, you either have a good or a bad. I'm going to try to slow it.
Yeah.
Explain. Versus that you're thinking about what you're doing.
Right. Yeah. Yeah, I think it's especially now that there's such a restricted page limit change.
I did not know that.
It actually helps us sort of notice before really fast. Because otherwise you're writing something 4 pages and then, oh wait, I need another page somehow. Or wait, oh no, I gotta go back to the small. So this year I felt like I really needed to know like how big we were gonna do things and then. I think it's the lower workload. Just a lower. Yeah. There was apparently a lot of complaints in the last cycle.
Give me a chance to.
Like, it ain't just like, there's so much
Right. Yeah, you definitely have to make them with this part in general.
Yes.
Yeah, exactly.
That's a crowd.
Yeah.
Sorry.
No, I mean, I think so. Generally, all I do is doing hoping to God, calibration.
But it's really much, you know, it's
in the end, I was 12.
Pretty
much, yeah. That's interesting. I mean, like, 3 or 4 of those have definitely.
Yeah.
Supposed to get supposed to wear one of these.
Like, yes, I think both of them work.
Sitting way up.
Oh, yeah.
Slip it in my pocket. Remember to take it back when I'm done.
There's a,
Oh,
not entirely sure which direction.
so this should change slides?
Pointed at that.
Oh, pointed at that.
There you go. And
Okay.
back.
Right.
And the pointer, I believe.
Laser pointer is which? This. Yep. All right. Thank you.
For a second,
Sure.
give an announcement.
Sure.
You talking to Laura?
She's the moderator.
Okay, welcome back, everybody. I wanted to remind you that we have a Slack space for this workshop, and there are some people already like posting, posting like questions, and please check it out to answer these questions and like put in their topics for discussion. We will have this Slack workspace available for another week. So when you, I know that everybody's tired now, it's Friday, but maybe next week you can go back and discuss that. And now you have an announcement as well? Okay.
Yeah, pardon my interruption. So last night, I'm not supposed to tell you this, but the LSST commissioning camera went on the sky for the first time, and the excellent people with the laser trackers and everything and pointing at the zenith and tracking and first dead reckoned to under 2 arcsecond images with, just, everything aligned by, by metrology. And now they're doing the intra and extra focal donuts and doing all the alignment and all the fun stuff. But it worked really well. And so thank you to the LSST team and the Rubin team.
Thank you. That's very good news. Now I would like to introduce the first speaker of this session is Abisa from NightLab, talking about faint red dwarf as photometric standards.
Thank you. As you can see from my first slide, several of the team who have been working on this problem now for almost 10 years several of them are here in the audience among us. So you will recognize yourselves as I go forward. So why do we need accurate spectrophotometric standards? And I think that the case has been made repeatedly earlier in this in this workshop in many different ways. Precision cosmology is one. We also need standards suitable for large telescopes, including having things embedded in surveys. And so you need to go faint as well as to be more accurate, or as accurate as you can. The other thing that has come up again also at this conference is the transformations between photometric systems across different platforms, from ground and space, different photometric systems. And if you have spectrophotometric standards, then you can generate synthetic responses through the system of your different telescopes and filters. So having spectrophotometric standards is therefore of great value. I put in this equation a little bit cheekily, but the point here is to really say that the responses can be broken up into that from the top of the telescope down to the detector. And if you're in a ground-based system, then you have to deal with the atmosphere. But these two terms are sort of separable. So you can have instrument response from telescope pupil down to the detectors measured in a laboratory-style way with NIST sources and NIST detectors. And that is already being done in several facilities. And I just wanted to put to urge things that when we send things up in space going forward, that as much of this kind of facility to self-calibrate should be built into them, because things change over the lifetime of a mission, and having something to change to look at how the throughputs have changed is very useful. Atmospheric modulation, we've heard a lot of talks already, requires a standard source of known ACD and brightness at every at various wavelengths, along with preferably a brightness at some fiducial wavelength in absolute units, and to have such a source ideally placed above the atmosphere. We've heard yesterday about a lot of experiments that are planning to do just that. While we wait, however, we were building up this DA white dwarf system to be the best possible substitute for that. And in the talk today, I will present a set of 35 different stars, DA white dwarfs, which we have calibrated, and I'll explain what I mean by that. You see the 3 Bolin stars in red, northern set of stars, and the southern set of stars in blue that have slightly different origins. But all of these things have been treated in the same way. We have got instrumental responses on the same footing for all of them in 6 different bands, going from F475W out to the H band using the WIFC3 detector of the WIFC3 instrument of HST. And for each of these, we can, and we have a range of temperatures and gravities for these objects. They express themselves differently in each of these bands. The Balmer features are also in there. And we model, we have models of across these temperatures and gravities that span a large range, and we compare them to our observations, and we find that the models and the measurements are seen to keep in step modulo issues that I will come up with, keep in step with residuals that are really, you know, in the near UV and visible are have a scatter of about 0.004 or less, and in the infrared detector, which is different, has something like 0.008. Now, in the bottom, you see these RMS values. These are weighted. These are weighted by the inverse of the errors, variance of the errors, and I'll come to that and what that means later in the talk. So this is sort of the punchline of the talk in case I get clipped by time. So and I'll go on from there. So why DA white dwarfs? Well, hot DA white dwarfs. So what we need is a set of standards at about 18th magnitude in V, or say, that would be in the high signal to noise dynamic range of surveys, let's say LSST, PanSTARRS, and ZTF, so that you don't have to do anything more in these broadband. These can be observed in the broadband. If you do that, you also make them accessible to 8-meter and 10-meter class telescopes. We choose things that are hot, very conservatively hotter than 20,000 degrees, because they're the least complicated to model. They're pure radiative hydrogen atmospheres. They're not vulnerable to pulsation. They have no convective things going on. And the models are fully characterized by just two parameters, effective temperature and log G. And you can decipher these parameters from their spectra through their Balmer features. So, for example, here is a Gemini spectrum in red and a MMT blue channel spectrum of a typical of one of our white dwarfs in blue, and you see how well that they can be fitted. In particular, the Balmer lines can be fitted with exacting accuracy. I'll qualify that in a little bit, and from that you can derive the temperature and the gravity. These principles were actually used by Ralph Bolin to define his 3 stars, which are at the foundation of the CalSpec thing. And so all of this really goes back to what Ralph did back then. And he compared, he had spectroscopy from FOS and STIS, and he was able to look at the, to derive the temperatures and gravities in the same way, and then compare them to the 3 stars, which have somewhat different temperatures and gravities, and to see that the observations varied in lockstep with what the models predicted. And this is at the basis of the CalSpec. Yesterday, the question came up about what defines the CalSpecs, and it's the physics of the white dwarf atmospheres, essentially, that does that. All right. So what we wanted to do was to repeat Ralph's experiment with 35 DA white dwarfs, as it turns out. We picked out suitable DA white dwarfs around the sky, typically between 16th and 19th magnitude, for reasons I've already explained. We examined a lot of them, so we could throw out and down select it to 32. That plus the 3 that Ralph has makes 35. We obtained spectra with Gemini, MMT, SOAR, whatever was possible, and we obtained panchromatic photometry in these 6 bands with HST with C3. This has a different detector, so slightly different color coded. So now, one of the things that we encounter here is that one summary. So we have sort of 3 ways of attacking it. We have the ground-based observations that get the spectra from which we derive temperatures and gravities. We have the HST observations that give us the photometry across bands. And if you want to have standards, you can't, have to do at least some due diligence. So we use the Las Cumbres Observatory to observe our candidates for us. And over different timescales, they have telescopes spread all across the globe, and we used those to check for variability, at least to the extent that we could. Right. So The problem is, of course, that when you get to faint, to the brightness levels that we have, which are faint, it puts these DA white dwarfs at several hundred parsecs. And then you cannot ignore the effect of reddening. So reddening has to become a parameter. So when you make you fit the photometry to the models, you have to allow for at least one parameter. In this case, is A sub v. We've used standard extinction. The fields where we've looked at don't have extreme reddening. The highest one has, I think, an AV of 0.3 or thereabouts. So instead, you see the different, there are some few different reddening laws that are put there, and you have to do this to accommodate that. The DA white dwarf sample, the equatorial and northern hemisphere objects were taken from SDSS and the Villanova catalog. That was the easy part. The southern DA white dwarfs, there was no Gaia at the time we were looking at these, finding our objects. And so we had to go and look at look for high propromotion objects, go back to the Sky Survey prints and say, oh, that one looks pretty blue. Let's go take a spectrum of it. And actually that wasn't so bad because it's about 50% success. And so we were able to gather up objects in the south and added 13 objects there. Right. So with the photometry, you can plot something like a chi-square or some kind of variability index. Here, for example, is our target star. If you take all the stars in the field and here's the magnitude and here's the index for all of them, you find that this one lies well within the lower end of this, so it's not variable. If you do it for another one, which is a variable, then you find that it deviates. So this was a good way to do it, and Annalisa here had a lot to do with setting this up and doing it. So ended up with this set of objects. A lot of attention was paid to removing correlated errors, and that was where a lot of the effort actually went. If you use TEF and log G in the notional way I said, any errors in that then propagate into deriving A sub v. And the other part is that given that some of the Balmer lines, certain temperatures can be very broad, a ground-based spectrum doesn't necessarily handle the continuum extremely well, so we had to invoke a Gaussian process to try and work through that and bring that into control. So Gautam Narayan was what was the person that worked these problems. Among them, derived a hierarchical analysis to disentangle the interdependencies in all of these things, and started out by fitting per object. By fitting per object, I mean that we get the object onto the CalSpec scale and then compare it. Compare those measurements against the model. You can also do something as fitting as an ensemble. Since we have 35 of these, we don't have to stick to the CalSpec scale. We can say, as long as we have instrumental magnitudes that are self-consistent completely, we can solve for everything together. And so you end up with a lattice of stars with different magnitudes and different bands, and on some arbitrary scale, which you then need to, which is uncertain to the level of one constant, which would take them to an SI traceable. So, whether it's through Vega or whether it's through Sirius. So, series of papers. Here's Annalisa's paper, led by Annalisa, about defining the full sample. Then solving for the ensemble, as I was saying, simultaneous fitting of an ensemble of objects. So currently we use, we're still building on this full hierarchical process. So currently we use the temperatures and log Gs from the single star by star analysis and we don't refit the spectrum, but you'll hear at the next talk by Ben Boyd how we're building up to that system of detail. So I will, here's Gautam's paper of, where was it, 2024. Here's Axelrod paper, which has all the stars and the spectrophotometry that you can look up if you wish. And once again, this plot, and here you can see that the RMS, when I said the weighted RMSs are low, well, that really says what the systematic agreement between our set of stars versus the models really is. And so, quick summary, last two slides, defined 32 new stars. RMS uncertainties are certainly sub-percent. The standards are spread across the whole sky. And, you know, you can, depending on if you're a ground-based observatory, you should be able, at any instant, you should be able to see at least two of them at air mass less than 2. If you wait, they'll go higher. They're being anchored by photometry above the terrestrial atmosphere, so there shouldn't be any seasonal or directional systematic errors in it. A couple of comments before I can let go. Analysis being redone with a newer set of models. The results differ by only a few millimag, but they haven't been published yet. Extensions into the UV and using STIS data are in the process, and I think Ben will talk a little bit about that. At this time, the project fully stands behind the results over the wavelength range that I showed you. Obviously, since these are models, can they be extrapolated later? We haven't tested them yet, so that's something that remains to be done, particularly in the infrared. So use any other extrapolations with caution until they've been validated. And I'll stop.
Questions? One online and then
Ruben, do you have David Rubin? Can you unmute yourself? Or do you want to?
Can you?
Go ahead.
Nice talk. How much do different RV values change the results?
Different RV. Oh, we in the directions we've looked, which don't have a lot, we're pretty much insensitive to changing of RV. I think that when you see the results from Ben's next talk, where he looks into the ultraviolet, there are some interesting observations from that I'll let him make that to answer that.
So yeah, following up on that, and then another question. So you said standard reddening law, which we can't agree on what that is. I'm just curious what reddening law you used.
R sub V of 3.5, we've used all three of them at some level, but I think we're using the Fitzpatrick.
Okay.
It's
Swapping them all out, trying all of them, we're going to try them.
Okay.
This one is just 3.1 constant.
Yeah.
Okay. And then with Fitzpatrick 99.
Yes.
Okay. Because RV means different things for all the laws. Anyway, the other thing is, I just thought it was funny. You're talking about atmosphere model errors, and I think you mean stellar atmosphere. And
yes, I mean stellar
ground-based atmosphere. When I talk about atmosphere model errors, it's something totally different.
That's the telluric atmosphere.
other question? Another one online.
Now Suzuki, go ahead.
Okay, so thank you very much for nice talk, Red. So retrospectively, did you see the time-dependent U3 0-point change, which was reported by Annalisa.
Sorry, what was, I didn't quite hear.
C3 0 points change.
The WIF-C3 0 points changed, but we didn't rely on that. What we did was, when we made our observations, we also observed Ralph's 3 stars at all times, and we used that to trace any variation of the 0 point. And we used the same amplifier and the same tiny piece around the readout point to minimize CTE effects. So thank you for the question. I think that it's an important one to make, that we made, that our measurements were done to mitigate the effects of changing response and other things as much as we could.
So what we did, we were observing the standards, the 3 primary white dwarf and the stars at different also epoch, and correcting for the time sensitivity change.
So from cycle to cycle, there were some changes, but
there were a few changes.
Yeah.
Carl?
So I'm curious, if you go back to your plot, the last plot you showed, if you have a, you know, I look at there and I say 625 looks really nice. Why do the rest have more scatter? Do you have an explanation or an idea?
Yeah, I think the thing is that we're fitting something that is allowed to move like this, and that just naturally becomes the fulcrum point. And so it's like a node in the fit, right? So
okay, so it's a fitting thing.
It's a fitting thing. It's not that there's something particularly magical about that, right? Yeah.
Awesome.
Yeah. Because we're allowing the brightness of every you know, we're yeah.
Well, for the infrared
every star has a different brightness, and we have to bring it to 0, and so yeah.
So the mean of 0 is by design.
The mean of 0 is by design. Yes. Yes.
Gotcha.
So if you don't have more questions, let's thank Abby again. So next speaker is Ben Boyd. He will keep talking about this network of standard stars and how to model that with hierarchical bias and technique.
Thank you. Hi, everyone. I'm Ben. I'm a PhD student from the University of Cambridge. And today I'm going to be speaking to you about the A model, or as I like to call it, DA model. It's a hierarchical Bayesian model for DA white dwarfs for spectrophotometric calibration. So this is just following on from Abi Sahar's talk. It's the same set of standards, but we're trying to fit all the data at once hierarchically. So that's the your spectrum and your data for all of them at once. So set of 35 is the 3 primary CalSpec standards that we've been hearing about a lot, and then 32 fainter white dwarfs. We've got 6 HST bands ranging from the UV to the near infrared for all of the sample. And then also we have optical ground-based spectra for all of the white dwarfs in the network. And more recently, we have STIS UV spectra for about half of the sample that we can also use. So as previously mentioned, already we've achieved sub% accuracy in Axelrod 2023 and Narayan 2019, but we feel that that's just using the optical data, but we still feel like we can do more by modeling the network hierarchically, by looking at all the white dwarfs together. The reason for this is that you can have improved constraints on instrumental systematics that affect the whole network, and there's a fully Bayesian propagation of uncertainties right from your data all the way to your parameter estimates. So what do I mean by hierarchical? I keep throwing this word around. What I mean is, referring to Bayes' rule, we've got the posterior is proportional to the likelihood times the prior, And what I'm saying when I say hierarchical is that the likelihood of the whole sample is equal to the product of the likelihood of each object. And you can use a graphical model to kind of visualize what I'm talking about here when I say hierarchy. Say you've got like data 1 and data 2 per object, you can infer some object level parameters, so that would be your y, whilst simultaneously dealing with some, say, nuisance parameters, gamma 1 and gamma 2, but you can also make population level inference on, say, this z parameter, which in our case might be something like a 0 point or a change in 0 point that affects part or the whole sample. So this is what the graphical model looks like for our model. As you can see, there's a lot going on here, but it's hierarchical in many ways. We've got, of course, the 35 white dwarfs. We've got coverage in 6 bands, and there's multiple observations per object per band. There's multiple HST cycles, and like I was saying, there's some spectra have, some objects have multiple spectra at different wavelengths. So it all fits into this hierarchy, but it's easier to kind of look at this as like the forward model. So what we start with is this SED grid that's recently been updated for better UV modeling. It's defined from 900 angstroms to 30,000 angstroms in these ranges, but it's a function of effective temperature and log surface gravity. And to begin with, we just interpolate this, so it's a continuous function of wavelength, log g, and effective temperature. And then after you're happy with that, you can then add your dust law. So we can try different dust laws in this. I stuck with Fitzpatrick 99 just so I can compare easier to what Axelrod and Narayan did, but we're trying different ones out. I've also tried Fitzpatrick 19 and looking to try Gordon 2023. But essentially what this does is makes your SED, a dusty SED, that is now a function of AV and RV, as well as the other parameters. Once you have your dusty SED, as you can see here, you then add some parameter that kind of acts like distance. It's not exactly distance, but it makes the SED dimmer at all wavelengths. And then you convolve it with your band passes, in our case, the HST band passes, and you get your synthetic photometry. Other things that are in our likelihood that we're also inferring are the 0 points in each band. As we were saying before, this cycle-dependent offset that you have across different Hubble cycles. We have a count rate nonlinearity that we're inferring in the F160 near-infrared band. You're also inferring dispersion in each band, and also there's a degree of freedom parameter that you're also inferring because we're modeling these using student T distributions instead of normal distributions, and the reason for doing that is because it's got fatter tails. So we find that works better. So that's how you do the photometry. This is how you do the spectra. You take that dusty SED from before, you apply some normalization, which you also infer, and then you convolve it with a normal distribution. And what that does is essentially Gaussian smoothing on the absorption features, because in reality, the resolution of your spectrum is never going to match the resolution of your theoretical model. So you need to do this smoothing. After you've done that, you'll end up with something that looks like this orange line here. And you can see there's still a difference between this and the black observed data. And this is kind of like a wavelength dependent systematic that is going to be different for every single spectrum. And Abby mentioned this before, you can treat this as like a residual and infer kind of this function. Previously, this was done with a Gaussian process, but what we found is that these functions are actually quite smooth, and the Gaussian process is quite expensive, and it's a little bit overkill. So we've recently switched to using a cubic spline, which is a lot cheaper and gives you pretty much the same results, which is great. This is for the same white dwarf. And the benefit of this, like I was saying, it's cheaper. You could say that the likelihood of the spectrum is equal to the product of normal distributions evaluated at each pixel. So it's, again, assuming IID, and it makes things a lot quicker. You can use this same kind of methodology as well for different wavelengths. So you've got this UV data here. It's the exact same method, you're just evaluating it at different wavelengths. So let's skip over to our results. The results that we get using only the optical data and with a freed up RV give us the best RMS residuals yet that we've had on this network. with less than 4 millimag. That these are the unweighted RMS values. And you can see there that we're doing around 3 millimag RMS from the UV all the way to the optical, and then the near infrared, we're doing 7 millimag unweighted RMS, which is great, and we're dealing with that count rate nonlinearity quite well. So let's take a closer look and see what happens to the residuals when we kind of change different parts of the model. This is what I was kind of referring to earlier with David Rubin's question. When you free up RV, you get a lower RMS, and that's predictable because you're adding a parameter, but also it's physically true that RV does not equal 3.1 exactly for all these white dwarfs. So that was almost expected, but what we didn't expect, or maybe we were hoping we didn't expect, is hoping to not encounter, was that adding the STIS UV data does make the RMS residuals worse in this case. So there's a couple of things that might be causing this. There may be some systematic that we're not modeling or understanding in the STIS UV data. It might be more that we need to improve the theoretical modeling of the DA white dwarfs at these UV wavelengths, or it might be that I've just not tried the right dust law yet. Like I said, I'm still to try the most recent one, Gordon 2023, so watch this space. A quick look at what happens to the SEDs when I add the STIS UV data. You can see that you've got quite a large change in the SED. Here, when I add the data, you've got like a 10% change around these UV wavelengths. Whereas if you compare just our optical work with Axelrod's optical work, you're only seeing about like a 1% change. So something's going on when we're adding this data that we still need to work out. A quick look at the parameter inferences. When adding the STIS data, you can see there's a little trend here where there's a few of the DA white dwarfs are being predicted as being cooler when adding this UV data, and also we're getting some kind of lower AV values when adding the data as well. So something that we need to kind of look closer at. So just taking our optical only results, we can look further at like the photometric systematics that we've added to our model. As we were saying, you do have some like non-zero changes in 0 point here that you can see highlighted. You can also infer a dispersion on each of the bands. You can see it's obviously larger with the near infrared, which is probably to be expected. You've got quite a high degree of freedom for the near infrared band, so maybe that's hinting that we could be okay using a normal distribution for that one. And we also infer that count rate nonlinearity that I was talking about. We get that as -2 millimag per mag, which is consistent with what Axelrod got in their work. So it's reassuring that we're getting similar values with quite different methods here. Quick look at the SEDs. These are also useful. These are just cropped. Like I say, they go from 900 angstrom to 30,000 angstrom, but they're useful not just for calibration, but for cross calibration. So we can integrate them under different pass bands. So here's what the RMS residuals look like for the DES data. So this is literally just taking our SEDs, inferring them, and get synthetic photometry for DES. You can see these are weighted statistics, and I did this more to compare to Tim Axelrod's work, and we get fairly similar results. Weighted RMS 6, 4, 6 in GRI, and it kind of gets a bit worse in the near infrared, which is understandable. So a quick shout out to Darcy Kenworthy's work. He's got a poster over here that's still up where they're using our SEDs for cross calibration of type 1a supernovae in a combined analysis. So we're really excited about that work that's already using the SEDs. Other avenues for this work is it's a hierarchical model, so you might as well make use of it, and you can kind of infer population level parameters. You can infer something like a population, like dust distribution of RV, or even like a tau. These are our results when doing that on this network, just to prove that it's possible, but these results shouldn't be taken too seriously because there's very heavy selection effects on these white dwarfs. They were very much cherry-picked, but it's more of a demonstration. It's possible if you give it a different set of white dwarfs in this framework. This work is very scalable now. It used to take over a day per white dwarf on a CPU. So that's 35 CPU days in total, but now we're taking about 30 minutes for the full sample of 35 on a GPU simultaneously. So great scalability improvements there. And that combination allows us to maybe apply this to a different catalog of DA white dwarfs, say some of the Gaia DA white dwarfs, and yeah, getting some more kind of more robust constraints on these population level parameters. So yeah, we look forward to doing that with this framework as well in the future. Final thing that I want to leave you with, we have spectroscopic coverage for at least some of the white dwarfs at most these wavelengths from the UV to the optical, but we're still missing spectroscopic coverage for the near infrared. And obviously you'd expect your near infrared results to be worse because then noisier measurements, but we still feel like there's room for improvement there if we get some near infrared spectra. And the model itself is completely trivial to add this data to the model. It's just evaluating the model at different wavelengths, just as I did with the STIS UV spectra. So yeah, when that data comes, we'll be ready for it. And yeah, I'll leave you with my summary slide and just say that this work should be out next month. So yeah, look forward to that. And I'll be releasing the SEDs as well. So thank you very much.
Yeah, first, let me just say I'm really happy to see you're using a hierarchical Bayesian model. David Rubin did that for the SNFs data, and we could ask all kinds of questions. Whereas before, someone had to sit in a room, should we do this thing or that thing? Yeah. We put it all in there and let the data decide. But as a cosmologist, one thing I learned to appreciate from the 3 fundamental CalSpec white dwarfs, that they were in the local bubble. Mm-hmm. There was no extinction. Yes. When you go and see what people do for extinction, they have to say, either I have a star I think has none, or I go to models. Those models depend on the calibration. So I always worried about circularity. Can you derive the extinction law by extending this method? So the calibration and the extinction law have to go together, as opposed to I pick this from somebody, fine RV, but that's a parameter, Fitzpatrick and CCM use it all differently. Right. The real law is more complicated than a nice, smooth function.
Potentially, I'd have to think about degeneracies there, but in principle, there's no reason why we couldn't add like a parametric dust law that changes even more to the kind of dust laws that are kind of set. So in my head, it would just be like adding extra parameters, but I would need to think about, yeah, that's obviously going to inflate your uncertainties if you don't have a set dust law. So in my head, I don't see why not. But yeah, I'd have to think about that a little bit more.
So is your question related to this, or because otherwise we have another one? Okay, so hold on a second. Yeah.
Yeah, maybe the dust extinction analysis might help. But yeah, it's really good. But when it comes to the UV, I guess, is it just a case of trying out more things, or do we need more data?
I mean, it's always nice to have more data. Yeah, I've only got STIS UV data for about half of these. It would have been nicer to have it for the full sample, just like the optical. I think it's a matter of just isolating different parts of the model and changing it and see how that affects our residuals. Like I say, I'm not an expert on any of the fields of theoretical DA white dwarf like SED modeling or dust laws, but like it just from a perspective of like it has to be one of these things. It has to be the data, the model, or the dust law. So that's the way I see it. So yeah, I'm just planning on like isolating different things and seeing where we're going. But yeah, we'd love more data, especially in like the near infrared as well. I'm sure that would help kind of break some dust degeneracies as well. So yeah.
Right. So I can say a little bit more about the dust law. I try not to use the word law at all when I do this.
Okay.
I call it a relationship.
Yeah.
And the reason for that is because the way to think about this RV dependent relationship is it's the average at that RV.
Right.
It's only an average. It's an observational average. And we know there's real variation around that average, and it gets larger as you get into the UV.
Yes.
So that's why I don't think you'll find an RV, an average RV relationship. See, I even do it that'll work well. So I think, and then you have to go to something more flexible, which is what we do in the dust extinction community. And that's something that Fitzpatrick and Massa 1990 formulation, which has 5 free parameters.
Okay.
So well, I've been already working with Ralph, and that will fit them significantly better, but for more parameters.
Yeah. So would that like increase the uncertainty on the overall?
Well, it's how you put it together. We could talk. There's a paper by Ed Fitzpatrick, I think in 2007, called Extinction Without Standards.
Okay.
So
Sounds
there's a
great,
pun
yeah.
involved there.
Yeah.
And to answer your question, yes, you can measure the dust extinction without doing flux calibration. If you measure you can do it with the classic method of a pair method, where you measure a reddened star and unreddened star that has the same stellar surface physics, i.e. you have a way of finding out it has the same log G, same T effective, same abundances. And then you just ratio the two in your system. You don't have to flux calibrate it. It can be in instrumental units, and you can measure the extinction curve. And that's
It's done in separate steps by different people. This would be a way to try to get it into one covariant matrix. We try to calibrate off of these stars. Maybe they're less certain because there's uncertainty about extinction. We want to put that into our error.
Any question on that? And then John, we can talk about it. We have a discussion about this topic.
Okay, so you say you're going to release the model spectra. Is it
the SEDs? Yeah.
The SEDs, right?
Yeah.
So is that with or without reddening, or both? And because I did download the Axelrod stuff, but I don't remember because it was a year ago.
But the Axelrod stuff will be with a constant RV equals 3.1. I can release whatever people would like me to release. It's something we should probably decide as a collaboration. But yeah, whatever would be most useful to the community, I can release.
So your primary release is the reddened models, so that you just compare it directly with photometry.
Well, in terms of comparing to the previous paper, I had to keep RV as 3.1. But in terms of if you want the kind of SEDs that have the lowest residuals on the HSD data, then that would be with a freed up RV. So yeah, it makes sense to me to release those ones. But if you are looking to compare to kind of other standards out there, then I should probably be consistent with them. So I'm happy to release both.
I at least like the one that allows the most direct comparison with the synthetic photometry in your paper, whatever that is. So I try to reproduce that and make sure that my code agrees with yours.
I think I'm just going to stick with the best results. So yeah, that would be the freed up RV version for synthetic and SEDs.
The question online. Question online, David Rubin, please go ahead.
So this is probably answered, and the answer is no, but I was just wondering if you use the recalibration spline for the UV, the STIS.
Can you say that bit again, sorry? If I use the recalibration spline for the UV? No, I don't. I didn't add any. As in before, so did I apply this to the data before giving it to my model? Is that the question?
Oh, the recalibration that you're doing for the ground-based optical. I was just wondering if you do it for the UV. I suspect the answer is no, but I was curious.
Oh, right. So do I add the flexible cubic spline? No, yeah, I do. Yeah, they both have a spline. Yeah. There's obviously a lot more going on in the splines inferred from the optical because there's a lot more systematics there, but I can choose to turn it off and on for this data, but at the moment with the results that I showed, it was actually, it was on. There's that extra flexibility of the cubic spline for this data. But if people think I should turn that off, I can turn that off. Turn it off. Yeah. So you're correcting. It's per spectrum because every spectrum has a different set of systematics. Well, at least for the optical, maybe it's more consistent for the STIS because it's.
Okay, we can keep talking about this at the discussion, which will be about white dwarf standards. Let's thank Bannigan. So the next and last speaker of the entire workshop is going to be John Debes, talking about checking the JWST MIRI absolute flux calibration using nearby white dwarf.
Oh, I see my talk even. Great. Just gotta wake it up. You made it.
Not yet.
Well, I could probably just talk without anything. I've done that before. Well, that's good. I can pontificate while the computer is thinking. So, well, doesn't want me to pontificate. Fair enough. All right. Nope, that's not it. What happened there? Different instance of. Boy, I hope this isn't eating my time. Okay, so I'm going to talk about a couple of programs that have been looking at white dwarfs in the mid-infrared. And I just want to point out that when we ignore or denigrate the interconnectedness of our fields, we do so at our own peril. And this work is dependent on probably most of you in this room, because you either calibrated one of the instruments or you reduced something in a high quality public archive, or you delivered something in an archive, or you made the instrument, or you helped launch it. So we need to remember that and be thankful for all the people who have done all the hard work, and for the people who just grab this data and use it for their own cool ideas. I think I grew up in a time of scarcity, data scarcity. We are no longer in a time of data scarcity. So it behooves us to just give our data as freely as possible, because good things happen, even if we don't do them ourselves. So why do I care about white dwarfs? I like them because they happen to sometimes have planetary systems around them. And about a quarter seem to be accreting low levels of dust onto their atmospheres. And that can also show up as an infrared excess in the near infrared or mid infrared, depending on, actually I'm going to get rid of this, depending on the temperature of the dust. So this is a picture of what we think is going on. There are these asteroids that come very close to the white dwarfs and shred and create dust, and that dust accretes onto the white dwarf. So that tells us something about planetary survival after main sequence evolution. In fact, MIRI is so damn sensitive that if you look at nearby white dwarfs, you can actually see planets in orbit around them at any separation, from the Roche limit all the way out to hundreds of AU. And Marianne Limbach has this wonderful paper, I encourage you to read it, that talks about why MIRI is a good choice for finding planets as either infrared excesses, which is what is being shown here. This is basically a spectrum of a white dwarf. It's in the Rayleigh Jeans tail, so it's just getting fainter and fainter at longer wavelengths, whereas the planets get brighter and brighter. We're talking about giant planets primarily, but these are extremely cold temperatures. The modelers don't know how to make planets at these temperatures. They can barely make Jupiter work. I'm exaggerating, but in any case, we don't really know what planets look like. They could be cloudy, they could be clear, but at any point, our best guesses of what planets are doing is that they start to show up at like 10 to 20 microns. They get to be a few percent, maybe if we're lucky, 10 or 20% excesses, but we want to go look for these things. So if you want a 10% excess, you need percent level absolute photometry, absolutely calibrated photometry, to actually see this in a significant way and convince the TAC that you want to then follow up your excess. And to sort of kick things off in cycle 1, Susan Mullally, who's here at the Institute, PI'd this wonderful proposal, GEO1911, that looked at 4 nearby bright white dwarfs that were metal polluted, 2 of which, by the way, were in Abby's talk just a few talks ago. We did very deep imaging at 15 microns because we were hoping to find planetary companions, and sure enough, we found a couple of candidates that are going to be followed up this spring. But we also took shallower images at other wavelengths, these 4 filters, which sort of spanned where we thought the photometry was going to be mostly photosphere, all the way up to 21 microns, where we hoped we might see planets as infrared excesses, and if not planets, maybe dust. And as an example of this, for one of our stars, these are the rough planetary mass limits with a few assumptions with MIRI imaging, and if you just look for an infrared excess, you can get down to sub-Jupiter mass companions in resolved orbital separations, but you even get a few Jupiter mass companions unresolved. And if you assume something about planets that get irradiated and sort of have have their thermal emission and then whatever they're getting from the white dwarf, you can actually get down to Earth-sized planets that are in very close orbits to white dwarfs. We don't know if they exist there, but now we can find them. And then these would be all the giant planets that presumably would survive post-mean sequence evolution. And sure enough, there's a non-trivial number of few Jupiter mass objects that we know of through direct imaging and other methods that we should see with MIRI imaging. So in addition, in cycle 2, I co-PI'd a survey program with Sabrina Polson at the University of Oklahoma. And we were just like, give us whatever white dwarfs you want to give us. We'll take a look at them at 10 and 15 microns. And this would be a very shallow, quick, what are we going to see? Because there's only a handful or so of white dwarfs that have ever been observed beyond 10 microns. So this was unknown territory. And in addition, there was another great survey led by Miriam Limbach, the MEOW survey. So these are just cutesy acronyms. This is the MIRI Excesses Around Degenerates survey. And I forget what MEOW was, but it's basically looking for planets. So Marianne was looking at 7, 18, and 21 microns. We were looking at 10 and 15. So they had about 20. We had 56 white dwarfs. Pretty much unbiased. We basically selected all the 25 parsec white dwarfs that we knew of, which is fairly complete. And then it was really up to the vagaries of JWST scheduling what white dwarfs we actually got. And so we got, this is one image of a white dwarf, pretty boring. You have some background objects. Some of them look like point sources. Others look like resolved objects. Some are even more boring. There's just nothing around for arc seconds. Some are near the galactic planes, so you get a little bit of dust coming in. And just luckily, it happened to be not in the dust background. Then you get things where a galaxy is nearby. And if this were a WISE observation, you would think this was a white dwarf with an infrared excess because it was confused. JWST is great. You don't have to worry about confusion. Luckily, this only happened twice in our survey, so pretty low odds at this point. Okay, so great. We have all this photometry. We start looking at everything. Do we have excesses or not? How do we know? What is our significance? Most of these were observed at pretty high signal to noise, and so our limit is not the photon noise or our photometry noise. It's how good is the absolute calibration. And of course, when this was first done, that was like 3%. And then just a few weeks or months ago, Carl actually told us the answer. It's more like 1, 2%. But I didn't have that answer when I started this, so I kind of did it myself to just basically prove to myself that I could do it and that I was doing at least as well as Gordon or Carl. And not screwing something up, because I didn't want to claim an excess that didn't exist. So the way we did this was we took a pretty much all DA, DB white dwarf sample. So we have the primary calibrator white dwarfs, and we had to throw in an A star because there's just not many white dwarfs that have been observed at 21 microns. When MEOW is all done, I'll start looking at those too. We added in our cycle 1 stars, so those are all DAZs. They range from 8,000 Kelvin to more like 18,000 Kelvin. And then I took the 3 brightest DAs from Meade, just because they were high signal to noise. And these, I don't even remember their temperatures.
So I tried as best I could, thanks to Misty Craycraft here at Space Telescope, to replicate the calibration reductions and the broad procedures that Carl did to try to replicate the calibration of the absolute flux calibration. And I'm sure there are minor differences. I don't think we necessarily used all the same choices in terms of thresholding or background subtractions or either dither combinations. I suspect that's probably at a percentage level at this point. But as we'll see, there doesn't seem to be a systematic problem with our detailed choices here. And so this is actually one of the cycle 1 targets in a 3-color image. There are 2 planet candidates here. Guess which ones they are. I'll tell you at the end. So these are just some of the details of what we did. Mostly we used the dither combined things. But in some cases, we were finding that like when you had smaller numbers of dithers, the photometry would be kind of like you get different answers with different ways of doing it. So we just looked at the individual dithers, averaged them, and assumed an uncertainty based on the RMS of the dithers. And that's actually what we did for all the Meade targets. So these are the results of just all the calibrators and our targets. The punchline is, yeah, looking good. These error bars are the true variation star to star. So this is just an RMS. There's no weighting, nothing else. So from my perspective, the dominant factor when you're doing things very, very carefully is your difference model to model and how well you're actually determining what your white dwarf parameters are. And I think that's probably what the limit is. So from here on forward, when I show you a significant excess, it's because it's more than like, I'm assuming a sigma of around 2%. Okay, so now we can do this with Meade. This is the full uncensored distribution of 15 micron photometric fluxes compared to model fluxes. And those were dictated by lots of pan-stars, APAS, Gaia, GALX photometry. You would fit an SED. You would make a prediction to the 10, 15 micron wavelength. You would then generate models based on those fits to do the proper filter convolution. You got to do all these things at this level. And you'll notice there's a spread, but there's this big central peak of objects, about 35. And if I just focused on the high signal to noise objects that are not deviating by more than 3 sigma from a like sort of population perspective, then I get a Gaussian fit to that population that has a sigma of 0.92 and a mode of 0.32. So what does this translate to when we talk about relative to calibration factors? It's actually extremely similar to what I got when I looked at 15 microns with my sort of high quality calibrator sample. So I'm pretty confident that the things out here are interesting outliers that are where my science are. So these are the infrared excess candidates, and these are most likely, we didn't get the atmosphere right for some reason. We used pure hydrogen or helium atmosphere models. Obviously not all white dwarfs are pure helium or hydrogen. And so if you have a combination of hydrogen and helium, you can get a different answer for what the longer wavelength photometry should be. So I think I know what's going on there. And I think I know that these are the interesting things that I want to look at. So hopefully we'll get to follow them up and confirm them as interesting outliers. But this is a very heterogeneous mix of photometry and models and all kinds of things. And we still get pretty much the same answer. So, whew. And just to convince you in detail, here are the 4 cycle 1 objects. This is one of the, Abby showed. And sure enough, I see a little bit of a higher than normal photometry, but everything else looks pretty good, and even all the way out to 10 and 15 microns. Good IR calibrator. This is another hot one. Lots of photometry, It's too bright for GalX and some of the visible, so we used the HASP data in some cases to do the UV. So you heard about HASP a couple of days ago. You know, I'm on the ISR, so I knew about this. So I definitely made use of it. And then this is a magnetic white dwarf, kind of weird. Oops, it's got something interesting going on. This is one of the planet candidates in that image I showed you, an unresolved excess. And then the other one is a resolved candidate. So this has 2 planet candidates for the price of 1 white dwarf. So hopefully we'll get to follow that up. And then this is another one of the ones on Abby's list. It has a very significant excess at 21 microns. So maybe you don't want to use this one. Sorry. Okay, so in my last 20 seconds, 4 seconds, we don't actually know what the excesses are because we have like 1 excess point. And so it could be dust, it could be a planet. Definitely Ash Messier, who is an undergrad at Smith, who's worked with me over the past summer, doing great work doing all this modeling, applying for grad school. So keep her in mind if she applies to your institution. But we don't really know what's going on here. So if you want to learn more, you just ask me in the questions since I've run out of time. So I'll leave my summary and take the questions. Thank you.
Questions?
We don't know about the populations yet to have an expectation of how many of these you should detect.
So yes, so from RV surveys and direct imaging surveys, we have some occurrence rate measurements. They are not exactly the same like orbital separation. Like the RV kind of craps out at 3 AU. Direct imaging kind of craps out at like 5 or 10 AU. No one knows how that all works. So it's very uncertain. They range from a few % of stars have Jovian mass planets to every star has Jovian mass planets. 10 to 20% seems to be reasonable. 25% of white dwarfs show some sort of evidence of planetary systems. 20% of A stars show debris disks. So I feel like the universal law for planetary systems is like with giant planets, this must be like 20-ish%. That's our excesses. These would all be sort of 5 to 10 AU away from their star, so they probably would have survived post-main sequence evolution. It seems reasonable. The Meow survey found, as you saw, like 3 or 4 out of 20. That's kind of in line with what we're seeing. But these all need to be confirmed.
So this is a comment rather than a question. You saw a problem with LDS749b, the DB white dwarf. That's also seen by NIRISS and NIRSPEC starting at about 2.5 microns. So you're probably going to have to look more carefully at your DB models and the data.
So it's looking because what I was seeing is that the model was, that the observed photometry was fainter than expected by like 10 or 15%. And I wasn't sure if that was just like I got a bad dither combination there and I have to go back and look at that more carefully, or whether it was a true issue.
So we were seeing about a 10% discrepancy in our scaling factor. So I don't know whether that goes the same way, but.
Okay, we should talk offline. Yeah, I need to look more carefully at that.
I think I missed something, because if I had a star with an unresolved 100 Kelvin excess, I would think debris disk, not planet.
Right, so let me go back to one of those figures. Thank you. So 2149. So the squares are the planet model. The black square is the actual data. And then all the other lines are different disk models. And so typically, we expect warm dust. So that would be disk at the Roche limit. That just is not so bright that it's exceeding our upper limits, but not so faint that it doesn't match the longer wavelength photometry. And that's basically like a scaled down version of almost every debris disk we know of currently around white dwarfs. We think that the main feature is that basically asteroids are disrupting at the Roche limit, and then the dust is going in. And so all the dust should be interior to the Roche limit. So at 100 Kelvin, it's at like 1/10 of an AU or further away. And that seems inconsistent with how we think everything should just be scoured clean due to post-main sequence evolution. You basically have to have things come from further away to get close, to really explain the dust. Yeah.
Online, do we have questions? Nothing? Okay, so let's thank John again and all the speakers.
Thanks.
So I invite Abisa for the discussion on the faint standard white dwarf. Yes. Oh, right. Sorry, Susanna first.
So before Abby comes up to lead the final discussion, I wanted to say a few words.
Because you started this whole thing?
Because apparently I walk in the door and I can't even drink my coffee. So you've probably noticed that almost every presentation has mentioned one word, CalSpec. And as you know, we started putting together this workshop 4 years ago, and then things happened. And here we are finally 4 years later. And at the time, we wanted to acknowledge Ralph Boland's contributions, particularly CalSpec. He refused to cooperate in letting us do a fest thing. He said, if you do that, I'm not coming. So we've effectively done a bit of a little stealth fest thing. He even gave a talk. So one of the things that I wanted to say on behalf of many of us is that to acknowledge this lifetime work that Ralph has put into giving us standard stars that we can work with. But also I'd like to acknowledge that over the years, he has mentored and collaborated with many of us, given very generously of his time. So that's all I wanted to say. So thank you, Ralph. And I'll buy you a beer just because of this.
I think I'd go one step Ralph, putting in the white dwarf models as the basis of the calibration, but attached it to a physical system, and it was nothing short of revolutionary, if I may say so. So that was a big leap in the right direction. So with that, let's talk some more about white dwarfs as standards.
Yeah. So I had a question that was left over from the talk before mine. You mentioned the dust, right? So I was wondering, had you also considered whether there was unresolved opacity from accretion? So as I mentioned in my talk, something between 25 to 50% of white dwarfs show some sort of silicate absorption in the UV. And so if they have one or many metals, that may show up as a slight unresolved opacity that you don't sort of resolve directly. Would you be able to account for that in the current framework?
Yes, potentially. Oh, sorry.
Yeah, I hadn't thought about that, but if there's kind of a way to parameterize this strength in the UV, yeah, maybe some additional flexibility to the model. I don't see why not. I could just add it to.
One of the secondary standards is a metal line white dwarf that's pretty warm, so it'd be similar, and maybe even put it in here. But it has a shell spectra, so you know where all the metal lines are in great detail. And you have low resolution spectra because it's a secondary standard. So this has looked at it like every 6 months for like 20 years. It would be a good test data set. Same with G191-B2B, because that also has metal lines in it.
Yeah, well, I mean, yeah, it'd be super interesting to kind of apply the model to that, not knowing that information and see how it affects my inferences. Yeah, there's different ways that I could add it into the model. I could add like extra flexibility, like you saw I did like a cubic spline thing, but maybe I could do the same for like an absorption feature, or you'd go the route of my theoretical SED, adding an extra parameter to parameterize what you're describing there, but that would more, I don't know, that would need some more conversation with the people that kind of make the templates.
That's just a general caution for white dwarfs in the UV because it's such a large fraction. I feel like you should probably either account for it or vet them in such a way that you sort of know what the abundances of the metals would be. So you can just throw that into your models.
Yeah, no, it's definitely
Makes a case for observing all of our stars.
yes. We want more data.
Yeah, I mean, that's the case for looking at all of them with costs, essentially.
Cost is steep.
But I think the point of, vetting them, how do you vet them? We have a list that's been out, but we really want to encourage people to use it. And sure, there will be some that we won't be surprised if there are some that show up. We've tried to do, some diligence by following them up. The photometric monitoring may not have been accurate enough. There can be differences, and they should be done in other wavelength regions. So,
but remember, it's not just absorption lines that you need to account for. If there are significant metals in the atmosphere, there's going to be absorption in the EUV. It's going to change the whole shape of the SED, and it can be quite subtle. So you need to. It's not just like adding a few absorption lines to your model.
It's true. Yeah.
Yes.
Oh.
Yeah, so I need some mentoring to connect this session in the white dwarfs with the black body talk of Nao Suzuki from yesterday. My perspective, not knowing as much as you all about this business, that's pretty simple models spectrally and things, but I don't see that. Like, what's the compare and contrast? What's my takeaway from simple spectral shape type of standards? Did we just not get there yet for the black bodies, or is there something wrong with them, or?
So those are featureless spectra that resemble black bodies, but they don't have a physical basis to put them in physical terms, which white dwarfs would be. So I think that I would put forward the idea that there is the combined use of the two of them would take this part. I don't know if now is still online.
But while he's joining, it seems like you just haven't put a physical basis on them, looked at them, and tried to calibrate them like we've done with the white dwarfs. Is that my takeaway, or is there some reason we cannot do that?
Say that again.
It's just that we just haven't gotten to looking at them and putting them on a physical basis. Is that right?
The calibration depends on a primary calibrator. They don't calibrate themselves, whereas the DA white dwarfs sort of do.
Sort of, but through STIS, and we looked at them, right? It's not. My takeaway is not.
But the STIS is calibrated with the DA white dwarfs through CalSpec.
Yeah.
Let me just respond to that.
So, Joe, I don't know what he did with the WISE data, but if you go and look at the original paper, the WISE data is kind of all over the map for those sources, and it illustrates what Avi is saying. If you don't have a physical understanding of the object, then you're at risk in applying it in spectral regions that you haven't actually calibrated with something else. So I think that's the issue with those. I think they're very useful for interpolating and that sort of thing. That's great. But as an absolute calibrator, there's work to do to actually understand physically what's going on.
Okay, thanks. So it's really that we have good physics to know what we're really looking at. White dwarfs. It's as simple as that.
It allows us to extrapolate.
Yeah. Thank you. That helps me tremendously.
Now says online that Aldo is modeled with black body stars. So there are models for those black bodies.
From Serena a little bit.
So they are white dwarf. They are white dwarf. That's not DA.
He doesn't agree with that, but that's.
That's what he said.
Helium white dwarf.
Yeah, there's a paper.
Maybe he can.
Yeah, go ahead and mute yourself. Would you like to comment more?
So if I may, so Aldo Serenari modeled the black body, so we got a physics basis. It can exist.
Modeled them as what?
As what?
Oh, he's
Can't
got
you
the
just-
yeah, he has
ahead
the white dwarf models for black body stars, and it's got the physical parameters. So please
So
go
they
to
are
my
white dwarf,
slide,
but what
and
kind of white dwarf?
it's a cool helium white dwarf. The temperature is right at the temperature, which is too cool for helium to show up, too hot for hydrogen to show up. So please take a look at his paper.
So the first author is Aldo, A-L-D-O. That's what he typed.
Serenelli. Serenelli is the last.
Serenelli is the last name.
First name.
No, Serenelli is the last name.
Yeah.
S-U-R-E.
So they're just white dwarfs
They are white dwarfs.
of a specific.
Yeah,
Pass them on.
my understanding is that they're black bodies because they follow, if you calibrate them, they follow a black body. But you calibrated them using standards. Correct me if I'm wrong now. So it's a bit of a.
But there are theoretical models that reproduce the black body shape. That's what the paper says. I have actually read it. I haven't read it in huge detail, so now should say it. But yeah, there is a theoretical basis for these black bodies. It's a white dwarf.
It's a white dwarf with what kind of atmosphere?
He just said that, right? It's. I'll repeat it just to make sure I understand it, right? He said it's too cool for helium lines and too hot for hydrogen lines, or did I get that reversed?
Too hot for hydrogen, too cold for helium.
There we go. Yes.
Okay.
We will actually read this paper.
I think the connection between what you're saying and the fact that there could be a model is for the DAs, you use the hydrogen line, so you don't have to get broadband calibration right. You just get it right in a narrow range.
Correct.
There are no features in the helium white dwarf black bodies, so you're calibrating for the temperature off previous photometry that someone has calibrated with something else. There's not a separate
I
feature.
think in this particular case, the theory tells you what the temperature has to be for them to have no lines. So the temperature is very, very narrow range by definition.
Understood, but you're saying that there's no way I could warp all the photometry and get a different temperature and say it's a black body with a different temperature?
No,
because
I'm not saying any of those things.
Yeah, so I think that's the difference, right?
And they're faint, so they aren't plagued by reddening. So there's that.
There you go.
Faint in the UV.
Yes, intrinsically faint. Here we are with the white dwarfs trying to deal with reddening because we need them to be faint enough to be in the right dynamic range for where we want to use them. That has all of these issues that have come up.
So
I think we're on top of, but still, not to have them.
So what we will need to, so that the community can start using these standard stars, do we need to do something like HST, JWST? What would be useful, like observing them with TIS, we were talking about, John was saying with COS, with Wi-Fi camera 3, infrared GRISM, and with JWST.
So I would like to hear more about what these mean. I have heard at least 4 different samples, I think, or maybe more. I mean, we already have some white dwarfs we can observe. So are we talking about a sample that is broad enough over the wavelength and has enough in it for supporting other observatories? I mean, what's the goal here? And that maybe would help define what we need in number, spectral coverage, etc.
Let's not forget the white dwarfs that were presented earlier.
Yeah. So we have all these stars. We have 17, right? 32 here. We have, I don't know, the perfect black body, it was 3 dots in.
Yes.
Yeah, so we need to decide, like, what do we have to do, what the community wants. Kevin and then Susanna, and then, okay.
So one thing about your sample is Ralph has been trying to model them in the same style as the brighter ones, and you get slightly different results than you have. So we have to evaluate what's going on there before we can, go ahead with them. And then other kinds of checks like that, especially if we want to go to longer wavelengths, need to be done before we can all go say, these are 100% wonderful, and we'll just use them forever, right?
I think that's work in progress. We
Yes.
certainly are cognizant of that, and we will go forward with it. But in the meantime, I think the purpose of defining these was that they would naturally be embedded in ongoing surveys, whether they because they lie all over the sky. So you don't pay a price for observing them as part of whether it be at LSST now or with pan stars and things, and with the satellites that are going up or have gone up that are going to do surveys. So they'll be there, and that was the sort of purpose. And the more we learn about them, the better we can use them to interpret, to apply them to the photometry.
I was just going to ask, do we need, is the question, what is a sufficient wavelength range coverage of all some of those stars? What is sufficient? Is it necessary to go from COS all the way to 30 microns, a complete set for some number of these? I'm just asking the question.
It depends on what people need to use it. Here is something that is built with the models. Are the models? I mean, we validated them in the range that we showed. Potentially, they're useful in the infrared. How useful would have to be validated by being observed, and so that's the effort to do that would, need to be motivated by people who see if they think that this may be useful for them.
Yeah, I think, of course, we use standard stars all the time during observatory operations. So that might be one option, to simply pool together the samples that you have. And of course, we have a variety of instruments covering a long wavelength range, going out to 20 micron at least from the ground. What would make it very relevant, and we're doing something in parallel, which we didn't present because it's work in progress, but it's very similar, where we have been looking at some white dwarfs like Shooter. We do the modeling, and we selected these specifically to be faint enough to become relevant standard stars for Mikado on the ELT. So they have to be faint. But what you have, of course, we could pick it up. We could include them. That's something to be discussed, how to do that in detail in observatory operations. And of course, then they would be observed on a very regular basis. Any variability would probably show up at some point. And as you said, we would then be able to have a better idea of how fit they are for each purpose.
Thanks. I just thought I would mention that in the next year, like in a year and a half, we'll have 2 epochs on all these samples of white dwarfs at varying levels of signal to noise from 0.75 to 5 microns, it seems like, from what I'm hearing, now sample, Abigail sample, and these others for free, basically from Spherex. That might be helpful in figuring out the next steps.
So I think maybe going back to a couple of comments before, can someone summarize concisely? And I'm gonna maybe put it on the chairs. Like, what are we trying to solve right now, right? Throughout the week, we heard about the accuracies of the observatories right now. We heard about Webb and the different instruments. The flux accuracies are between 1% and 2%. ALMA, they're targeting 5%, but they're doing a lot better than that. Like, are we trying to expand again CalSpec or our sample of standard stars to lower, to get to the below 1%? I feel like right now it's not clear. Are we trying to expand CalSpec because we want below 1% from UV to far infrared? Like, what are we trying to do? What is the main question? I think it might help to put it at the top, and then we can discuss from that point. Did that question make sense? And does someone have an answer?
It made too much sense. All of the above.
Different people have different goals.
Right. And so because I keep hearing like, well, we can have this sample and solve that. Like, so we don't have one major umbrella. We can't say we're trying to go below 1%. We don't need to go below 1%.
Yeah, for cosmology, we need to go a factor of 10 better than that.
Right. I mean, if that's what
not
we're
everybody
trying to
does
achieve.
cosmology.
Not
so
everybody,
maybe
exactly,
doesn't have
not everybody needs that.
that accuracy.
And so for cosmology, you don't need from UV to the far infrared.
That's right. So that's what I'm saying. You'd end up with a Venn diagram of this wavelength range needs this, and this science case needs this. Where do they all overlap? Right. And you'll see it's heterogeneous. Yeah, there is one point. No, we don't all overlap for the same goal. Right. I wouldn't put it on someone who wants to study planets to be good to 0.1%. We want to do that for cosmology. Well, why make that the goal for someone who doesn't need
And
it?
so I think if that's the case, right, if that's the nature of the problem, that's why things advance very disjointly, right? That's why we're struggling to put everything together.
Yeah, he doesn't care whether the total brightness is unknown to 2%. He cares about colors being accurate to millimeter. Right. And so the white dwarfs the experiments were conceived to deliver to that, and they are attached separately to the absolute scale, right? And how accurately you want to tie that to them may depend on somebody who's doing habitable worlds and cares about the absolute value. So it depends on the science direction.
There's also a comment of that.
Tell me I'm not chair.
Well, while that's happening, I would just comment that while the ground-based surveys may be focusing, or even space-based surveys for energy may be focusing in the optical and near infrared, I might say, that doesn't mean observations at other wavelengths doesn't help them. For example, if we tell them 4 of those white dwarfs you're using have debris disks, maybe you shouldn't use them because it's probably screwing up your optical. Can we get a more complete and robust sample that would? So I don't think we should see this as a disjoint problem personally. I think it is very interconnected.
So following up on that, a recommendation, I've seen this happening in other communities, we can form a SIG, Science Interest Group, under NASA and NIST, where we actually sit down as a community, as a group, and write down a guiding document for the community. It's been done in the past for other science purposes, where you map the different science cases and put down the specific definitions of what is what and how you measure, etc. And that could be a guiding document for the community in the future, moving. I don't know what the answer is, but maybe that's a good start. And I can sponsor that if that's the path you want to go. Just need to make a decision.
Yeah, and another way where already some of us were talking about that maybe we should organize this kind of workshop a little bit more often, or once every 5 years, like especially now that things are going fast. Like, and Roman is gonna be in space in a couple of years, and serving Rubin just started serving. So maybe we want to have another of this workshop next year, next summer, or we want to create like a group like the high energy people are doing, where they have regular telecons. Then I don't know which cadence you want to do that. So in between the workshop, you can still communicate, and that will be very efficient. But of course, at the beginning to set everything this up, it will require some work from different members of the community. So we need to decide that, like you volunteer to contribute to this group, for example, but we need to find other volunteers.
I propose we make a group. Do we have any seconds?
Just one. I'll second that.
There we go.
That's one group or more?
Well, we need one at least.
Step one, make one group.
So we can draw the Venn diagram.
Two, agree to disagree.
Yeah, I think Christian made that point that with the atmospheric workshop that we're going to have within a half a year or something, we have formed the first working group of that order. But I think I'd just like to repeat what I said early in the discussion when we started, that yes, I'm very much in favor of doing that, but you need to have the commitment from a core group of people to actually drive the process. If you cannot and work, thank you. And if you cannot get that, and I would argue we need to have it here and now, because once we are back at our home institutes, there will be many other interesting things. So we need to do this here and now.
So calling for volunteers.
I would sponsor it. You guys decide, mix it up.
Two.
Can you get the funding?
I will cover some of the funds, yes.
Who's writing the names down?
Yeah, I
can write the names down.
Please. My hand's up to volunteer Carl again.
The computer?
I have institutional support.
With colleagues like this, you know.
Kevin, you wanna say something?
Just come to me at the end of this discussion and I'll write you up on together.
Thank you. So Kevin wanted to say something?
Yes, but it's not related to what we were just talking about. So the person I want to ask is preoccupied.
Preoccupied.
Abby?
So I have a couple of questions. If he's going to yes, for you. So one is a speculative question. Do magnetic fields have any factor in this that we have to worry about in these models? But separately from that is a more practical thing. We talk about forward modeling, but we have to get together at some point and make sure that different people get the same result from their forward modeling. And of course, your stars are a wonderful benchmark for that, because you did all that stuff. You got all that very nice space telescope comparison, and it would be nice for other people to make sure that they can reproduce that, including me personally. And so that's something we haven't talked about, is how to verify the accuracy of your forward modeling, which we talk about at intervals. But there's no guarantee that everybody gets the same answer unless you sit down and compare something and make sure that everything is good. So that's a separate thing, but it's important.
So I don't know exactly what you're asking for. I mean, if you run the same code on the same numbers, you'll get the same answer.
Yes.
People have different code with different assumptions. They will give you a slightly different answer.
That's what we want to evaluate. Does my code give the same result as yours, and you've got this stuff? That's why I was asking for exactly the same models, so I could run them through my code and make sure I get exactly the same synthetic photometry result. right? And then we're all on the same page, and we know that we understand at some level what we've done.
And if they don't match, then either something, some different physics was put in, or, I mean, trying to unravel that.
No, I'm using your models to duplicate your synthetic photometry compared to the observations. So it's just the codes.
Yeah,
right? We do that. So that first we get the codes to match, and then if we have to go on somewhere else, we do that. But we want to make sure our codes match to the level of precision we want. Otherwise, we're going to have problems when
We'll talk about this offline. Yeah.
Okay, I think it's quite late. So if you want to volunteer for this working group,
Just come to me at the end and I'll let you know.
what's your name? Sorry.
What?
What's your name?
Elliot.
I contact Elliot and let him know, please. And thank you very much for attending the workshop. I hope you enjoyed it. I'm sorry for the technical issue we had the first couple of days with no projector, but everything was solved. And hopefully we will meet again in about 1 year. I don't know where, but thanks everybody. And I want to thank also all the members of the SOC which are here online or not here, and for helping in the organization of this workshop. Thank you.
Please come over here if you want to register for the SIG.